So this is a question that's going to ask us to link enthalpy, delta H, and entropy, delta S, and then we're going to use that finally to work out the minimum temperature at which a reaction is feasible. One thing that I would say is that when you do these kind of questions involving enthalpy and entropy, is go through and underline the units, because the units of entropy are joules per Kelvin per mole, but the units of enthalpy are kilojoules per mole. So joules, kilojoules, joules, kilojoules, and we're going to use that when we come down to this part here. So the question says, calculate the standard enthalpy change for CaO in the reaction. So going back to AS, delta H of a reaction is the sum of all of the enthalpies of the products minus the sum of all the enthalpies of reactants, and the products are calcium and CO2, so it's 0 plus minus 110. Remember, it's an element, so its delta H of formation is 0, minus, square brackets, calcium oxide, minus 635, plus carbon, 0, because these two things here are the reactants, and your calcium and your carbon monoxide are your products. Put that into a calculator, the answer you get is plus 525 kilojoules per mole. So it's an endothermic process. Next part says calculate the standard entropy change for CaO reduction in the equation. Similar type of equation, so it's delta S of a reaction is the sum of the entropies of the products minus the sum of the entropies of the reactants. Putting the numbers in, so the entropies of your products are 41.4 plus 197.6. Ticking them to make sure I've used them. Then the entropies of your reactants are calcium oxide minus 39.7 plus carbon, and putting that through your calculator you get 193.6, and it's positive. Do you expect it to be positive? Well, you do, because the entropy of the system is increasing, and it's increasing because you go from a solid and a solid, which are low entropy species, to a solid and a gas. Remember, a gas has got much more entropy than a solid. It's much more disordered. There are more modes of freedom. Last part, it says calculate the minimum temperature at which carbon reduction in the equation is feasible. So for this you need to use the Gibbs equation, which is delta G equal delta H minus T delta S. And for a reaction to be feasible, for it to happen, the Gibbs energy has to be 0 or less than 0. So we have to say delta G got to be less than 0. So if we put 0 in that equation, we say 0 is delta H minus T delta S. And then if we manipulate that over, pulling the T delta S over, you get delta H equals T delta S. Hence, delta H divided by delta S equals T. Now we're going to put the numbers into this. So we know that our enthalpy change is plus 525. And we're now going to put in our entropy change. But the trick with the entropy change, as we started and talked about, is this is in joules, but this is in kilojoules. So to make sure that the units are consistent, you need to divide your entropy by 1000. So 193.6 divided by 1000. Okay? Because that's in kilojoules and that's in joules. Your entropy is in kilojoules, your entropy is in joules. Putting those numbers into a calculator, the number you come up with is 272,712, sorry. Now the question of this is units. Now, throughout of this we've used Kelvin. So the units will be Kelvin, because the entropy terms are given in Kelvin. So that means your temperature at the end is going to be given in Kelvin.